मा विद्विषावहै। ओम शांति शांति शांति।
We had started our discussions on an alternate formulation for stiffness matrix in a triangular element. Remember, we had already emphasized the importance of triangular element, and hence it is important that we understand what we are in for when we do triangular elements. Unfortunately, in the industry, again I am just emphasizing the importance, unfortunately in the industry, if you really look at how people do finite element analysis, most of them do not have the time to put a very proper mesh. They do not have the time to put, for example, a hexahedron element. So, what they usually tend to do is to rely on this kind of what they call as automatic mesh generation. In fact, I have seen from my experience about 70 to 80% of the people, why maybe more than that also, people use only automatic mesh generation. Okay, that is what is given in the software. But there are a lot of pitfalls in it. It is nice, it is good to use it because you can finish your job very fast, but there are a lot of pitfalls to it, and that is the reason why we are going through this kind of derivations. Yeah, let us now look at concentrate on this triangular element. We are now going to develop, or rather look at, what we call as a simple coordinate system. What is a coordinate system that we are going to give, or an alternate coordinate system? Let us say that I am looking at a point P. Okay. Now, let me join, P can be at any point, whether here, 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 or whatever it is. Okay. Let me join the three vertices of the triangle, okay, and call as A the area of this triangle, and A1 and A1 to be the area of that piece, that is area of the triangle P 2, 3 and so on. So, this is called as A1, this is called as A2 and this is called as A3. Is that clear? So, A1, A2 and A3. Now, let me say that the point, any point P at this point or any point P can be expressed by means of a coordinate system, say psi I, which is equal to AI by A. Is that clear? Now, that means that this point P can be expressed by means of coordinate systems psi 1, psi 2 and psi 3. Immediately, yes, I can see in your face, immediately there is a question that we are in a plane and we need only two coordinate systems independent, the basis, all of you know some linear algebra, okay, the basis in a plane, there are only two what we call as I and j are what are required. Now, you are talking about three coordinates. Okay. Now, where is the lacuna? Yeah, I can understand immediately, that is the question that comes to your mind. Exactly, that is correct. So, in other words, psi 1, psi 2 and psi 3, which are A1 by A, A2 by A, A3 by A, are not independent. In other words, psi 1 plus psi 2 plus psi 3 is equal to 1 obviously. So, in other words, this brings us to an important concept that psi 1, psi 2, psi 3 are related, and that they can be used as the first set of equation to solve or to express x and y in terms of psi 1, psi 2 and psi 3, okay, to express in terms of psi 1, psi 2 and psi 3. So, in other words, okay, I can write down say for example x to be, okay, psi 1 into x 1 plus psi 2 x 2 plus psi 3 x 3. So, my whole idea immediately, remember what we did, we tried to develop a mapping between a new coordinate system which we had put, okay, few days back, and x and y. So, I am going to develop the same thing. So, I am going to say that, say let us say that x is written as x psi 1 x 1 plus psi 2 x 2 and plus psi 3 x 3, right. Similarly, I can write down y to be psi 1 y 1 plus psi 2 y 2 plus psi 3 y 3. So that taking these three equations, I can write them in the matrix form as say 1 x y 1 x y is equal to psi 1 psi 2 psi 3. What are these things? Simple, 1 1 1, that is the first equation, okay. Second equation is x 1 x 2 and x 3, third is y 1 y 2 and y 3, okay. So that, so let me call this matrix a matrix. If you like another name you can give it, but be careful you should not confuse with other matrices that you know. So that psi 1 psi 2 psi 3 now can be expressed as A inverse now. A inverse can actually be expressed in a very explicit fashion. A inverse can be expressed in terms of an explicit fashion, okay. Let us say how we express A inverse, let me do that here, okay. I mean just for is equal to 1 by 2A into x 2 y 3 minus x 3 y 2 x 3 y 2 y 2 3 and x 3 2. That is the first row. So, x 3 y 1 minus x 1 y 3. What is y 2 3? Y 2 3 is y 2 minus y 3, okay. Y 2 3 is y 2 minus y 3, okay. People who know it by heart, this is not a problem for if you know how to do a inverse of a 3 by 3 matrix, y 3 1 and x 1 3. This is available in any standard textbook. So, next is x 1 y 2 minus x 2 y 1, okay, y 1 2 and x 2 1. Okay, not very difficult to remember because 2 3 3 2 3 1 1 3 1 2 2 1, okay, and similarly 2 3 3 2 3 1 1 3 1 2 2 1. So, 1 2 2 1 1 2 2 1. Okay. Now, what is that we have achieved? The first step is that we have achieved, we have determined or we have put down one what we call as a coordinate system. Now, I am not happy with only this because I want to convert this into a natural coordinate system and follow the procedures which I know. Okay. In other words, I do not want to stick to 1, 2, 3, but can I convert it into a form which is very similar to the form which I had for my quadrilateral. How am I going to do it? Simple. What I am going to do is I am going to say that let me call psi 1 is equal to a psi coordinate system. Let me call psi 1 is equal to psi. Okay, just wait a minute till I write that, and then psi 2 is equal to eta, so that psi 3 becomes 1 minus psi minus eta. Let me write like this. Okay, so that I still stick to my psi eta coordinate system. I am right. I am defining, what is that I am doing? I am defining psi and eta to be like this. Okay, psi 1 is equal to psi, psi 2 is equal to eta, so that psi 3 automatically becomes 1 minus psi minus eta. Okay, that is my first step. I have defined what all I have done. I am very simple. Whatever I have done is only took a what is called as an area coordinate system and defined the my natural coordinates psi and eta in terms of this area coordinate system. But my job actually begins there. What is my job? See, let us trace, let's keep always in mind what we are trying to do, so that you don't get confused. See, what is that we are doing in isoparametric element? I am recapitulating for nth time, but does not matter, because this has to get into your mind and when you follow this derivation. First is I put one coordinate system, one natural coordinate system. That is the first step I am doing. The second step is what I am going to do? I am going to write, your determinant is comes later, you know. I think what I should do is at the end of the class, what I am going to do is I am going to give, or I am going to ask you to give me a framework to code this whole thing. See, that is why I told you in one of the classes that coding is important, because you will understand all the steps very clearly. So the next step is determination or writing down the shape functions. See, that is important. Now I can't use obviously my 1 by 4 into 1 minus eta 1 into 1 minus I, those shape functions which I had used in the earlier classes. I can't use it. Okay, now I have to write down shape functions for this. Once I write shape functions, then I determine what is called as the Jacobian through the determination of dn. Okay, is it clear? So then I determine the dn value, then I determine Jacobian, then I determine B matrix, then I determine stiffness matrix. Okay, so that is how we proceed. So this is common, whatever be or however I do it, these steps proceed. Okay. Now in fact what I am going to do is to illustrate this for a 6-noded triangular element, so that you will understand that the procedure is exactly the same. Okay. Now for a linear triangular element of what we have given, I can straight away use this to be n1, this to be n2, and this to be n3, n1, n2 and n3. Okay, shape functions. But let us now move, that's not very difficult and you can work it out yourself, but let us move to a slightly more difficult, or not difficult actually, but a different type of element. See, so far we have been looking at what are called as linear element or first order element. Whether I put these 3 nodes in this element or the 4 nodes that I had put for a quadrilateral element, okay, the quadrilateral element becomes what is called as a bilinear element. Here it is a linear element. However I put it, you can, it's very obvious that we are looking at only linear interpolations. On the other hand, let us look at an element which looks like this. A 6-noded triangular element. Okay, 6-noded triangular element whose nodes, note this carefully how I am defining 1, 2, 3, 4, 5, 6, whose nodes I am defining it as 1, 2, 3, 4, 5, 6. Okay. Now, what is the peculiarity of this element? Though I have written it as straight sided, okay, in the xy coordinate system, can someone guess? First of all, how many nodes are there? 6 nodes are there. So, I have to necessarily go above my linear interpolation. What is that we are doing in isoparametric element? We are shapes are also linearly interpolated for that previous element, because x and y, remember I had written it in terms of psi 1 and psi 2. In fact, u and v are also I am going to write it in the same fashion. Okay, x is equal to n1 x1 plus n2 x2 plus n3 x3. That is what I will write. Right. In this case, also both x as well as u, or both x and y as well as u and v, I will now write down by a polynomial which is more than, the orders of which is more than linear. Okay. It would become in this case quadratic. So, what does this physically mean? What does this mean? It means that in my xy coordinate system, this triangle what I had put can take what shape? Take a shape something like this. Okay, because these chaps are defined by quadratic interpolation, right. Now, what is the quadratic interpolation that we are going to use, or in other words, see, please note that I am going to use the same shape functions, same coordinate system psi and eta, or psi 1, psi 2 and psi 3. Okay, either way you can use psi 1, psi 2 and psi 3, or psi and eta, the relationships have already given, right. So, now how am I going to express the what I call as the shape functions, because I am interested in the shape functions to express my shape of the element as well as u and v. So, I write this as, say for example, how many shape functions are going to be there? Obviously 6. So, I am going to write this as n1 is equal to, say, psi 1 into 2 psi 1 minus 1. Now, just look at that for a moment and tell me whether it is okay with you. Just check whether it is okay with you, in the sense that does it, I mean I just put it down by inspection, by experience you can write it down like that. You can see that what is that I should get? I should have n1 to be equal to 1 at node 1, and at all other nodes it should be equal to 0. Okay, that happens quite nicely there. And n2 is now given by psi 2 into 2 psi 2 minus 1. Right, and n3 is equal to psi 3 into 2 psi 3 minus 1. And n4 is equal to 4 psi 1 psi 2 and so on. So, n5 is similarly 4 psi 2 psi 3, okay, and n6 is equal to 4 psi 3 psi 1 and so on. Right. So, what is that I have done? I have essentially put down a what I would call as a natural coordinate system, okay, by means of areas, okay, and express them either as psi eta, or you can keep it as psi 1 psi 2 psi 3, either way you can substitute now in terms of psi and eta in this as well, okay, and written down for a 6 noded quadrilateral a shape function which 6 noded triangle, a shape function which happens to be quadratic. Is that clear? A shape function which is quadratic. Now what does this mean in terms of, or what is the improvement I have done? What is the improvement I have done here? Pardon? Strain, beautiful. So one of my major drawbacks in my previous say derivation, our previous discussion, one of the things which we said is that that triangle which I had put down had a problem basically because it was a constant strain triangle. Now what will happen to this? What will happen to this? Now it is quadratic. Now you need not even work out equations. You can have a feel and just tell me what will happen if displacements are now expressed in terms of psi squared and so on, okay, psi I squared and so on. So it will become linear, beautiful. So if we call the previous triangle which we had as constant strain triangles, CST as people call it, then this triangle we call this as linear strain triangle or LST. Is it clear? Okay, fine. So what is my next step? What's my next step? Once I have written down shape functions, what is that I am going to do with these shape functions? Yeah, dn, correct. Why not you try and write down dn for this? Okay. Next step is, because I am moving towards Jacobian, okay, moving towards Jacobian. So I have to calculate or I have to write down dn. By the way, what would be the size of dn? I mean, I am talking about the complete dn. 6 by 6 by 6, 6 by 2. Okay, you can write down the coordinates as x1 y1, x2 y2, x3 y3, x4 y4, or if you want to write it down as x1 y1, x2 y2 completely, either way you can write it down. Okay, but you have to be careful as to how you write down. After all, Jacobian is given by dou x by dou psi and so on. Okay, now so that's the way you write down for this as well. Okay, now we can calculate dn, put down dn, okay, and then you can calculate, okay, you can write it down in terms of psi and eta as well. Then you can calculate dn. I am not going to repeat all that because I am sure all of you know it. And once I calculate dn, then what I am going to do is to calculate j inverse and then substitute it into my stiffness matrix expression, from which I can calculate the stiffness matrix. Right? Till that point I leave it to you. I am sure you can all work it out, okay, but I am going to stop there at that point and look at the stiffness matrix, how I am going to estimate the stiffness matrix. Now what is the peculiarity in estimating the stiffness matrix? I can't use just like that -1 to +1, -1 to +1. I have to keep them as an area coordinates. So the type of integration that I am going to use is different there. Okay, it is to be an area coordinates. Now I am not going to again go into the details of it. A lot of textbooks have this information. So that is, in other words, the exact say Gauss point quadrature and other things that are used. Okay, I am not going into the details of this for the triangular element because it is a big chart. Okay, any standard textbooks, like for example R.D. Cook has listed down what are the Gauss points and the corresponding weightages and so on. Okay, so I would like you to look at that book for weightages and so on. But on the only thing I want to mention is that if it is A phi dA, okay, then then this can be written as sigma wi ji phi I, where the values of the w's, okay, weights and the corresponding positions, what are called as the Gauss point positions, okay, the point positions, can be obtained from these tables. Okay. They are not just multiplication, it is not 2 by 2 and so on, they are, I mean, they are quite involved. Okay. I am going to leave that because that is going to consume a lot of time to look at them, but it is anyway available in standard textbooks or standard even tables that are available for it, you can work it out from that. Okay. So, in a nutshell, what it really means is that it is possible to express or possible to calculate the stiffness matrices of any type of element through the same procedure. Okay. What does that mean? It means that whether I am going to what I looked at as a constant linear strain triangle or higher order elements, then also it will be possible for me to express or to calculate stiffness matrix in the same fashion. Just as a small exercise, let us now go into what we call as a higher order element, okay, for a 4-sided element. Let us look at this for a 4-sided element. Okay. In other words, let us look at an element which looks something like this. Let us now look at a higher order element of this shape. Okay. Now, how many nodes will there be? Why 8? Okay. I specifically asked this question basically because all of us have a tendency to say, okay, initially that there are nodes only on the edges. Okay, right? Pardon?
Serendipity elements.
Yeah, you are prompting, okay, what I am going to teach beforehand, but nevertheless, see, this is 1, 2, 3, 4 which we have, which we know. Okay. Now, why I asked this question, though he prompted beforehand a type of element that I am going to teach, okay, but what is important or what should have come from you is a different question. What is it? I am going to give you a minute to think about it. How did we arrive at the shape functions for this element, 4-noded element? Forget about this curves, just 4-noded element. Just look at that element and how did we arrive at the shape functions for this? There are 2 ways in which, if you remember, we arrived at, or 2 in fact 3 ways. One of the very mathematical way or mathematically correct way, okay, I do not mean others are wrong, but rigorous way in which we arrived at is by Lagrange interpolation, right. In fact, we interpolated it from a 1-dimensional case, we interpolated it in 2 dimensions, remember that, okay. We interpolated it in 1D and 2D. Now, this is for a linear. Go back and look at your Lagrange interpolation. Okay. Suppose I want to go to quadratic, next step. Next step. How many nodes should be there? How many nodes should be there? 3 nodes. Okay. Now, 3 nodes, if I put 3 nodes like this, okay, on one side, is this complete? And can I write down Lagrange interpolation from this? Because what did we do in the linear case? We wrote in this case, we wrote interpolation in one side, we wrote interpolation in the other side, and then we combined them. Now,
You can do that, but at n1 it will become 0. So n1 will become 0 at
no, wait a minute. Okay, wait a minute. Now, I want linear in this direction and linear in this direction. That is how we got in this fashion. Okay. Here, if I have to do it, it has to be quadratic throughout. If you say from a Lagrangian interpolation point of view, okay, then actually I should have one more node in the center. Okay, one more node in the center. okay, then only there will be quadratic in all the lines that I take. Okay. So this that is why we call this as a Lagrange element, a 9-noded Lagrange element whose interpolation function can be determined from Lagrangian formula, Lagrangian interpolation formula. So the first thing that you should keep or I mean take away from your mind is that there should be elements only on the side, right. There can be elements also nodes only on the sides of the elements. There can be nodes also inside, and such an element becomes a Lagrange element. It is a very good element, it behaves very nicely and so on, but only thing is cost becomes very expensive when you keep using more nodes and so on. So there is a variation to Lagrange element which are called as serendipity elements. Okay. The difference is that I do not have one node at the center. Okay. There is no node at the center of a serendipity element, and many times the shape function for a serendipity element is written by inspection, okay, by inspection, by intuition. Is it clear? Okay. Now, so what is the difference between Lagrange element and a serendipity element? A Lagrange element has a node at the center and its interpolation functions can be determined straight away from the Lagrangian interpolation function in a similar fashion as we did for the one-dimensional case. Serendipity elements do not have a node at the center, okay, and the shape functions are written by inspection. Is that clear? That is the first thing. It is not, I mean, of course it is not very difficult to write it, okay. Maybe for a minute you can see how do you write it, or I will give you a minute to think as to how, whether you can give a procedure. First of all, can you give me a procedure as to how I can write the shape functions for such an element, or in other words, the clue is, can we proceed from the shape functions of the 4-noded element? Can we proceed from the shape functions of the 4-noded element? Okay. Now, okay, let me give you why the serendipity elements become important later, okay, but let just look at it and see whether it is possible to proceed from the shape functions of the 4-noded element. Okay, just look at that element. I will give you a second to just see how this can be done. Okay, I mean I just want a procedure from you. Yeah, the first thing is that let us see how this shape function looks like for a 4-noded element. See, that can be done something like this. See, let us say that is an element. I just make it lie down, okay, and just plot the shape functions. How will it look like? Something like this. Okay, this is a, right, do you understand? It is a n1 would be a linear surface such that, what is this value? That is this value 1, okay, and shape functions are 0 at all other places. Now if I want to adopt this, what should I do? There are two things I should do. Okay, now I have put down nodes at these places. Okay, I hope you understand that this is a surface like this, sloping surface. Okay, now in fact I think it would be better if I put it like this, maybe the picture becomes better. Sorry. something like that. Now, what is that I should do now? I should remember that there are nodes at these places, okay, and make this shape function go to 0 at these places. So, that is my first thing. Okay. How do I do it? Usually how it is done is something like this. I will put down a shape function, say for example 5, 6, 7 and 8. Let me call them as 5, 6, 7 and 8. Okay. Now, how does my shape function n5 look like in the same mode? Okay. Now, it looks something like this. Okay, that is the one, that is the shape function for this, okay, and it would be something like this at the center and goes to 0 at other nodes. Okay. So, it is quadratic in one direction, okay, for this, and linear and goes like that in the other direction. Or in other words, n5 can be written as half into 1 minus psi squared into 1 minus eta. Half into 1 minus psi squared into 1 minus eta is a good candidate for shape function for n5. Is it clear? Now, when I put down this candidate, just check whether it satisfies all my requirements. n5, see that they are zeros at all positions. Do they become zeros? At all other nodes, obviously. Okay. Now, what is for n8? What is for n8? Similar thing for n8. How do I write down for n8? So, this is the psi eta coordinate system. I am going to come to that again, I think I forgot one of the things to be said. Psi eta coordinate system, and how do I write this? Right, 1 minus eta squared into 1 minus psi. Okay, before I proceed, I think one of the comments which I left out is that please note psi and eta coordinate itself is a curved coordinate system. Okay, they are not straight lines, obviously, they are curved coordinates, because after all psi and eta we chose as one of the curves in the element, and hence psi and eta itself are curved coordinate system. Is that clear? Okay. So, what I did was, yes, you can say how did I write it? I wrote it after considerable experience, okay, looking at it, saying that okay, this can be quadratic, so 1 minus eta psi squared. So, by lot of things, maybe you would have taken 1 hour to write it. I just like that wrote because I knew what is the thing, right. But this was written purely by inspection, by looking at lot of candidates and saying, look, this looks like one candidate which can satisfy whatever I want. Okay, n8 can also be written like this. Now, what is that I want to do? I want to now put down one new n1 in such a fashion that this n1 can force the values of n's at these nodes here go to 0. Is that clear? So, what does it mean? It means that if I can make it go something like this, okay, the shape go to 0, okay, then I can get a new n1. Or in other words, what it means is my previous n, okay, for a quadrilateral element should go to 0 at this point and that point. Is that clear? Should go to 0 at these 2 points and should not, two things, it should go to 0 at these 2 points and should not now get to non-zero value at all other nodes. Wherever those fellows are 0, they should remain the same. I mean, look at that very carefully. I have written down n5 and n8 by inspection, okay, by saying that 5 and 8, it should be, you know, n should be equal to 1 at 5 and 8 respectively, should go to 0 at all other positions. So by inspection, by considerable experience, I have written n5 and n8 like that. Now what I want to now do is to force this n1. I will tell you what is important later, now why we are writing it like this later. Now I want now these n's to go to 0 at these 2 places, okay, and retain zeros wherever it is going at the same level. So what does it mean, or is there any clue from it? You understand what I am saying? Is there any clue from what I have done or what I have said? So in other words, can you now play around with n1, n5 and n8, because n5 and n8 are not zeros at the places where I want it to go to 0, 5 and 8. Okay, is that clear? So can I now play with n5 and n8 so that I will make this n1 go to 0 at 5 and 8 as well, and not make it rise above 0 at 2, 3, 4 and so on. No, wait, have a look at it, don't rush. Do you understand? So now I have this much value, I have to make this fellow, okay, multiply it or by something, subtract it. How do I do it? Right, is that clear? Right, I have to make this fellow, this length here go to 0. Okay, the way I can do it is to do something with the shape function. Yeah, how do you, or what do I do? So that is equal to 1 according to this n5. Say for example, take only 5, n5. So one place we will make it go to 0. So what is it that I do? What is the value here? 0.5. 2 n5 if I put, what will happen? If I put 2 n1, then what will happen? Wait, it's good, you know, I'm very happy with these answers. If I put 2 n1, what will happen to n1 at 1? It will become 2. It will become 2. So I can't use 2 n1. Yeah, come on, someone said that answer, n5 by, if I put n5 by 2 alone, correct, that's it. So n1 my linear fellow minus half n5. Purely, I'm spending time because purely by inspection, by intuition, you know, I mean that's why it's called serendipity element. Okay, serendipity is what? What is serendipity? By accident, by chance, right? Okay, so this element came about by chance, and shape functions are written purely by inspection. Yes, there is one more way of writing it, by our what? By straight lines, right? Okay, we will do that later, okay, because this just gives an insight as to how the shape functions look like. That's why I'm going through this. Is it complete? Is it complete? Hey, you have not completed it. Yeah, but you have made one fellow go to 0, this fellow go to 0, but you have not touched this fellow. What? So what do I do? Because what happens to n5 at this position? It is 0. Is it plus? Why should I have a plus there? Minus n8 by 2, period. So minus n8 by 2. So, n1 is equal to that linear, our linear n1 L minus n1 sorry n5 by 2 minus n8 by 2 will be my new shape function. Similarly, see look at this, this is quadratic one side and linear on the other side. Okay. Now, similarly I can write down, I am not going to do it now, but you can say that similarly you can write down for n2, n3 and n4, n6 and n7, right. Is it clear? Okay. Now, what is the advantage of writing like this? First of all, coding becomes very simple. See, for example, you may decide to use higher order elements at some places and stick to your linear elements at some other places. So, there will be a transition element. Okay. So, what will be the transition element, or how would it look like? How would it look like a transition element? Say I am going to have 8 noded elements here, okay, all these 8 noded elements. Then I want to now go to a linear element in the next step. So, I will have an element like this. Look at this element, look at that element. That element has 5 nodes, okay, 5 nodes, 3 one side, other sides have 2 each, okay, 5 nodes. Now, if I develop my shape function like this by inspection, by writing down n5, knocking off from n1 such that making it 0 at other positions and so on, okay. Now, what will happen if I have an element like this? Is it first valid or not? Sorry, is it valid? Can you write down now shape function for this? Okay, say for example 1, 2, 3, 4, okay, 5 is absent, 6 is absent, 7 is absent. So, I have only 8. Is this element, can you handle this element? Of course, you can handle it. Okay. How do you now write the shape functions for this? You write down first the shape function for n8, okay, the same fashion as we did right now, half into 1 minus eta squared into 1 minus psi, right. And then what do you do? Knock off from n1 half n8, period. Knock off from n1 half n8, okay, and from what else do you knock off? n4, knock them off, so that you will now get a new element itself, 5 noded element, okay. Shape functions can be very nicely written. Is that clear? Okay. So, what we have done essentially right now is to write shape functions for a quadratic elements, okay. I have written down by inspection, it will take some time to sync. My suggestion is go and think about this particular thing, okay. And now we will extend this concept, okay. By the way, what do I do now with J? I mean, what next step? Write Dn, write J, B transpose, dB, T, J, d psi, d eta. So steps are the same, okay. Steps are no more different. We will comment. Is this clear? Any questions on this? So only thing is, if you know how to write a shape function, period, the whole things just follow. So I am not going to emphasize more on this. The only thing, major emphasis that is required is on our numerical integration. Okay, there are a lot of issues on numerical integration. We will talk about numerical integration, the issues involved in numerical integration in the next class.